Okay, moving on to our last problem. As we finish out our exponential models, we're going to look at another exponential model. It's continuous, but we're going to look at decay. So we've talked about exponential growth as continuous, which is modeled with our natural exponential function. And the same thing here in our next example. So we're looking at continuous exponential decay, which is modeled with our natural exponential function. So it says a 500 milligram sample of radioactive decays following a continuous exponential decay model to 34 milligrams after 30 days. All right, find the daily decay rate and give an exact answer and not a decimal approximation. Okay, so let's talk about our model first. So again, with it being a continuous exponential decay model, A of t equal to our initial amount, we'll call it a sub 0, times e, say natural exponential function, e to the rt, right, is that function. Now with it being decay, we know r will be less than 0, be negative. So we'll notice that as we solve this. Now what are we given in this example? All right, we're given an initial amount. Go ahead and write that up here. A sub 0 equal to 500 milligrams, right? That was our initial amount. Right? And then after 30 days, we were given the amount. So let's write down our other piece of information. So we're given a time value. After 30 days, all right, we had 34 milligrams. All right, so that implies A of what? 30 is equal to 34. All right, mg. So let's set up that function and go solve it. So that implies, as we build our model, A of t, so 34, equal to our initial amount, right, which was 500. Not 5,000, but 500, times e to the r, which we don't know, we're trying to find, times t, which is 30. R times 30. So we got a natural exponential model. We know how to solve it, right? We got to solve for r. All right, and that means we got to go isolate the exponential term. So our next step will be to get rid of that coefficient, right? 500. That we have here. Let's go ahead and divide that out on both sides so we can isolate here together. So that implies 34 over 500 is equal to e to the 30r, right? R times 30. We'll go ahead and write that as 30r. All right. Now, with that said, we're looking at our next step, which is using our log properties. Right, we got to get r out of the exponent. Now we would like to be able to get the same base and drop it down using exponent properties, but we know we can introduce logarithms. We're going to take the natural log, right, on both sides of the equation, and then we can use our shortcut property, right, our same base or composition property, and bring down the exponent. So just like we did in our previous example. So let's go ahead and show that. Now, real quick, let's go ahead and give ourselves a little more room here. All right, so as we're looking at this, let's go ahead to our next line. So this implies, so as we introduce our logarithms, so natural log of 34 divided by 500 equal to, again, whatever we do on the left side, we must do to the right. We got to do log base c. Remember, this is our abbreviation for our natural log. Log base c is ln of e to the 30r. Right? And we like that because, and again, I'm going to write that property down here beside it. We know that log base a of a to the x power always simplifies to x, right? That's what we want to look at, right? In our next step, we want to simplify. Same base rule. There's log base e of e to 30r. So those wash out and simplifies to the exponent. So what we have right now in our equation is the natural log of 34 over 500 equal to 30r. And now we're just solving a simple linear equation. So we'll divide out our 30 on both sides, and we'll have our answer, which is our rate, right? We were looking for that decay rate, that daily decay rate. So R, our daily decay rate, is equal to the natural log of 34 over 500 divided by 30. Now that's our exact, right? There's the exact rate. And we mentioned this is a decay model, so it should be a negative, right, value. So let's show that. So what is the natural log of 34 over 500 divided by 30? And you might, like we did in our last one, maybe you want to simplify 34 over 500 and make that look a little bit better. And let's clear out our last problem. 34 divided by 500, that is 0.068. So real quick, if you want, let's go back to our model and let's go ahead and plug that in. Right, so this is equal to the natural log of 0.068 divided by 30. So again, it does simplify a little bit. With that said, all right, let's go ahead and find out what we get with that value. So let's go back to our calculator. Let's type that in. So the natural log of 0.068, which is 34 over 500, divided by 30, right, our time value. And I got negative 0.0896. As you can see, negative approximately 0.09, right, was our percentage, which is negative, 9%, if you're talking about as a decimal. So remember, it's a decay problem. I knew we'd get a negative value. All right, so let's go ahead and write that in. Then we got exact. I always like to look at the decimal it gives us. So negative 0.09, and we rounded, so approximately negative 9%. So there's our decay rate, right? Now again, that's approximation. Of course, this is our exact. All right, and let's go ahead and take that into our next problem. So part B says write the equation of this exponential model using the exact values. So using this rate value we found. So again, that's amount in T days of this radioactive substance here is equal to the initial amount, which was 500 milligrams, times e to the R. Well, our rate was the natural log of 0.068 divided by 30, right? All that multiplied by t. So there's our function. There's our natural exponential function, this continuous exponential decay model. All right, we found that rate. Now I'm going to use that as I go into my last part here, part C, and let's talk about half-life. So half-life, all right, that's asks us when our amount is equal to 1/2 of the initial amount. 1/2 of a sub 0. So a question in this problem, we know that a sub 0, our initial amount, was 500. So we want to know when we get 250 milligrams of radioactive. So that's our question that we're looking at. When do we have half-life? So let's go ahead and solve this equation. So when did we get 250? So our amount in the end needs to be 250, half the original being 500, times e to the, again, natural log of 0.068 divided by 30, right, times t, right, my unknown, my time value. I'm trying to find half-life, how long, right? We want to know what the time is, and of course, this is in days. So as we work on solving this, our first step would be to isolate the term. All right, go ahead and we got to solve for t. So keep in mind what we're solving for. So that means we need to isolate the exponential term. And to do that, we got to divide out on both sides. That's 500. All right, which what do we get? What is 250 divided by 500? That reduces to 1/2, right? We're trying to find half-life. So 1/2 is equal to E to the natural log of 0.068 divided by 30, right, times T. So now we've isolated, we can now take the natural log of both sides. So we can use our log properties and bring down the exponent where T is, we're trying to solve for. So let's go ahead and do that. So in our next step, we've got the natural log of 1/2, the left side of the equation, equal to the natural log on the right side of the equation, which is E to the natural log of 0.068 divided by 30 T. All right. And again, this was our whole goal, right? As we look at our simplifying property, we can write over here on the side, we know log base A of A to the x power simplifies to x. So using that rule, right, here we got log base E of E, same basis. So we can drop down that power. So we have the natural log of 1/2 equal to what? Natural log of 0.068 over 30 T, which means we have a linear equation to go solve. So let's go ahead and divide out that coefficient. So on both sides, right, we'll multiply by the reciprocal, right? Same thing. But yeah, we're dividing that out. So this gives us T value. So T is equal to the natural log of 1/2. And we know that dividing by a fraction, right? We go ahead and multiply by the reciprocal. So times it by 30 over the natural log of 0.068. So that's what we're ready to type in. So keep in mind, this is natural log of 1/2 times 30 over natural log of 0.068. So let's see what we come up with for our time value. Let's pull up our calculator here. If you want, let's write that down on a paper side so we can look at it as we put it in the calculator together. So again, I got the natural log of 1/2, right, times 30, right, divided by natural log of 0.068. I got 7.74, right, rounded, and that's days. So there's our answer. So around 7.7 days, almost 8 days, right, we're going to have half-life. We're going to have half the original amount of radioactive. Right, we started with 500 milligrams. Right, we're going to end up with 250 in a little over 7 or almost 8 days, we should say, 7.74 days. So yeah, that's half-life. So you'll see some of those examples, right, half-life examples we've been working through. So that's it. That's our review. Those are our important topics from this unit we've been studying. So I hope they will help you as you're preparing for your test.